Hey folks, welcome back. In this video we're going to look at our second application of fields, which is the cyclotron. So let's get started. Now it says here, when electric and magnetic fields are combined in certain ways, many useful devices and measurements can be devised. And we see this at play in the cyclotron, which was seen in higher physics. So it firstly says this device accelerates charged particles such as protons and deuterons. Scientists have discovered a great deal about the structure of matter by examining high-energy collisions of such charged particles with atomic nuclei. The cyclotron comprises two semicircular D-shaped structures called Ds, as shown below. So the picture here shows a setup of the cyclotron, where we've got our source of particles in the middle, in this case it's protons. We've then got our two hollow D-shaped structures which form this kind of circular shape. And we've also got a high frequency alternating supply. And we're going to now look at these steps explaining how the cyclotron works. So first of all, it says there is a gap between the Ds across which an alternating voltage is applied. So the alternating voltage is applied between the Ds, and this will set up an electric field between the Ds. It then says towards the outer rim there is an exit hole through which the particle can escape, and this has a radius of big R. From this point the particle is directed towards the target. So here's the exit point where the high-speed proton beam can leave in this case. It then goes on to say that charged particles are generated at the source and allowed to enter the cyclotron. So in this case it's protons which can go on and enter the cyclotron. It then says every time an ion crosses the gap between the Ds, it gains energy QV due to the alternating voltage. And that energy is work done energy, W equals QV. For this to happen in step, the frequency of the alternating current must be the same as the cyclotron frequency F. This can be achieved by using a high-frequency alternating supply to change the polarity of the Ds, which in turn changes the direction of the electric field across the gap. If the electric field direction was the same at all times, then the particles would not continue to move. Now looking back at the case for the protons, you can see they move towards this D on the right hand side first of all, and then they curve round to the left hand side. But this means that initially, in order for the protons to go to this right hand side D, it must be negatively charged on this side, and this D on the left hand side must be positively charged. And that's so that the positively charged protons are attracted towards the negatively charged D. However, since the protons are going to gain energy across the gap due to the electric field, they're going to accelerate as well. And to get the protons to move from the right hand side D to the left hand side D, we need to change the polarity of the Ds. In other words, we need to change the sign of charge on the Ds. So if the right hand side was negatively charged to begin with and the left hand side was positively charged, the high frequency alternating supply will switch it so the right hand side is now positively charged and the left hand side is negatively charged. So this positive charge on the right will now repel the protons away, and the negatively charged left hand D will now attract the positively charged protons towards it. And this changing of the polarity is going to keep happening so that the protons can keep accelerating back and forth between the Ds. Now you can see that as they increase in speed, their radius of curvature also increases, and we'll see why that is by looking at some equations later on. But for now I just want to show you a couple of quick simulations to help you visualize what's going on. So in our first simulation here of the cyclotron, you can see we've got the two Ds in blue, and we've got the electric field in green across which the particles will accelerate, and in this case we've got positively charged particles. So if we click play here, you'll see we've got some acceleration between the Ds, and then we've got some curving, some changing of direction inside the Ds. And that's because we've got magnetic fields inside the Ds, remember. And so when the particles have enough kinetic energy, enough speed, they're going to leave the accelerator. And now we're going to look at what happens when we double the strength of the electric field instead. So this time we've got fewer spirals, we've got a higher kinetic energy of 60 joules compared to the 54 joules from before, and the particles were able to leave the accelerator in a much shorter time. And that's because if we double the strength of the electric field, then the particles will accelerate at a greater rate between the Ds. Lastly, I'll show you what happens if we double the strength of the magnetic field instead. So this time you can see we're getting a lot more curving inside the Ds, i.e. due to the stronger magnetic field. So you'll see we've got a lot more spirals here compared to both the cases that we just looked at, and although the particles took a lot longer in this situation, they left with a much greater kinetic energy of 202 joules. Now another simulation I've got here helps to highlight the changing polarity of the plates. So if we click play here, you'll see the protons accelerate between the Ds and they're changing direction inside the Ds. And we've got this changing polarity back and forth from the positive to negative to positive and so on. Going back to the notes, it says from earlier we have already seen the following expressions. F equals QB over 2 pi m and R equals mv over QB. So this was a relationship between frequency, charge, magnetic induction and mass, and this one was our radius of curvature equation, R equals mv over QB, where we've got radius depending on mass, velocity, charge and magnetic induction. And we can see that radius and velocity are directly proportional here, so that's why as velocity increases for the particles in the cyclotron, then the radius of curvature increases, so we get those spirals of increasing size. So therefore we can say radius increases as velocity increases, and we can say at the radius of the outer rim big R, velocity will be a maximum, and therefore if we rearrange this equation for radius of curvature for V, then we get QBR over M, so V max is equal to QB big R in this case divided by M. And we could say that the kinetic energy on exit of the cyclotron is equal to a half mv squared, where the V here is our V max expression, so if we substitute this in here and square it, then this comes out to Q squared B squared R squared over 2M. That's all for this video folks, thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.